Today we're going to look at work and energy, which is chapter 5.1 in your book. And work is really any method of transferring energy from one object to another. Work in physics is only done when an object moves through a displacement. The key here is that the displacement and force must be in the same direction, or same parallel direction. So we can also have positive work if F and D are in the same direction. And therefore negative work if the force and displacement are in opposite directions. Work and energy are both measured in units of joules, and we'll talk about that in a moment. Units of joules, and you can remember that. I always remember joules for work and energy, because if you think about all the people that have lots of or control the world's energy tend to have lots of money, and they can buy lots of joules. Energy is a term that's given to something that has an ability to do work, so it can produce some sort of change. It's a very general term, and we're going to talk about two types here, which are in this unit both kinetic energy and potential energy, which we'll get into in some other units. So let's take a look at, let me erase this, formulas. Work, which is capital W, is equal to force times distance. And again, key thing here is that work is only done when they're in parallel directions. So work has units of joules, and a joule is equal to a Newton meter, which you can see by looking at the units of what work is made up of both force and distance. Force is still measured in newtons. All forces, any type of force, can be measured in a newton. Remember that a newton is a kilogram meter per second squared. Distance or displacement is also in meters. So let's take a look at a couple of examples and how do we use this. So in the first example, we have a force of 50 newtons, and that's acting east, and it acts on a 600 Newton box. The box moves to the right 2 meters. We want to know how much work is done. So again, remember, go back and start doing your old Givens list. So what do we know? So we have a force applied, which is 50 newtons, and this is to the right or east. Acts on a 600 Newton box. Well, that's the weight of the box, so that's 600 newtons. And it moves a distance of 2 meters. We want to know what is the work. So if we do a little sketch, again, keep doing your pictures. So we have force of gravity going this way. We've got our normal force, and we have this applied force of 50 newtons. And it moves this way 2 meters. So since we want to know what work is done, we know that work is force times distance. So it's moving to the right, so we need to use the 50 newtons and the 2 meters. So we simply end up with a force of 50 newtons times 2 meters, giving us a work done of 100 Newton meters, and that 100 Newton meters is a joule. So the work done then is 100 joules. Okay. So let's take a look at another one. So another problem, a little more complicated. Okay, so here, example 2, we have a box, and again, let's go through and start listing our givens. We'll underline things. We have a 20 kilogram box. It's accelerated at a rate of 5 meters per second squared. and the box moves to the right at 2 meters. We're looking for how much work was done on the box. So given 20 kilograms. Kilograms is a unit of mass, so mass is 20 kilograms. It's accelerating at 5 meters per second squared to the right, and it moves a distance of 2.0 meters. Again, we're looking for the work. So if we do our quick little picture, again, here's our box. This has a mass of 20 kilograms. And it's accelerating to the right. And it moves a distance of 2 meters. And let's go ahead and put this acceleration up over here. We have 5 meters per second squared. So there must be some force acting this way for it to accelerate that way. I'm going to leave off the weight and everything because that really doesn't matter in our problem. It's only dealing with this force and this acceleration. So here we don't have a force. It's not given to us. But we do have a distance. So let's see if we can figure out how to get to what we want. So work is equal to force times distance. Well, what do we know about the force? If you think back to Newton's laws, we know that force is equal to mass times acceleration. So work can really make you mad sometimes. So work then, we have mass, we have acceleration, we have the distance, and now we can substitute those things in. So we have 20 kilograms times your acceleration of 5 meters per second squared times your distance of 2 meters. So the work then is 20 times 5 times 4, so you have 100 times 2, giving you 200 joules of work. So remember, we're still building off of old concepts, so don't lose track of those old concepts. Let's take a look at one more example. In this last example, I'm going to help you get started, but I'm going to leave a couple of the answers for you to finish off. So we have a box that's pulled to a rope pulled by a rope to the right, making an angle of 30 degrees with the horizontal. If the force on the rope, let's underline this 30 degrees, if the force on the rope is 20 newtons and overcomes a frictional force of 50 newtons, we want to find each of those following. So here, I'm going to do a picture before I do the givens, just to make sure I sort of have my idea what's going on. So I have my box again. This 200 Newton force is going at 30 degrees above the horizontal. So if I take and sort of lightly draw my axis on here, whoops, I've got this 200 newtons going this way, and my angle of 30 degrees above the horizontal. And it also says I have a frictional force acting this way of 50 newtons. And it doesn't give us the weight of the box here. I must have left that off. So let's add in here that the force due to gravity, which I left off in my problem statement, is 800 newtons. So we want to know, what is the work done by the applied force? Well, before we do that, again, we need to we left off a couple of things. We also missed the distance on here, so let's put the distance in here. Okay, let's make this distance. Let's go with 6 meters. So we have a distance that it moves this way, 6 meters. Okay, so the first thing we have to do, because we don't have the forces and the distance going the same direction, we have to find the x and y components of the 200 newtons. So let's do that first. So the force in the x is equal to then the 200 times the cosine of 30 degrees. And the force in the y direction will be 200 times the sine of 30 degrees. Okay. Again, remember 200 sine 30 is 100. And 200 times the cosine of 30, I believe, is 173 newtons. So now let's take a look at part A. Part A say we want the work done by the applied force. So the work done is equal to FD, where these two have to be in the parallel direction. So we have the X, so really it's going to be Fx times D, which is 173 times 6 meters, and 173 times 6, 173 times 6 gives me 1,038. And again, it's in work, so that's in joules. So what I'd like you to do is see if you can then take and finish off parts B, C, and D. Remember that the net work is equal to F net times D. So see if you can do B, C, and D and submit those on the form below.